Hi, my name is Abdul Dakkak. I'm a kernel developer at Wolfram Research. My talk is called the Wolfram Compiler Advances. And in this talk, I'm going to talk about the advances that we've made in the compiler in the past year. I'm going to talk about the type system, the runtime system, as well as how to express certain logics in the new compiler to develop more functionality within the Wolfram language.
Okay, so a disclaimer. So most of what you see is kind of internal detail. So this stuff won't be exposed to the users unless you really want to. So this is how we write it's mostly how we write the compiler, not like what you would probably do. The title of this talk was like Compiler Advances or something. So the objective of the compiler, if I want to summarize it in a few words, is we want people to write Wolfram code. We don't want them to write C++ or assembly programming. We want them to write the Wolfram code. In fact, the entire Wolfram compiler is written in Mathematica itself, in the Wolfram language. We want people to get similar speed to as if they're handwriting C++ code. So kind of remove the need for stuff like library link and all of that. There should be predictable performance guarantees. So nothing where if I have a list of 1,000, I get 2x performance, but if I increase the list to 2001, I get 1x performance. That's kind of weird behavior. We don't want that. And we want it to be explainable that the semantics and the design decisions should be explained in kind of easy kind of guidelines. So nothing like, this part of the code behaves in some way, and then a different part of the code behaves in a different way. So I'm going to kind of talk about some of the kind of background material. So the current hardware, which is what we're targeting, is multi-core. So there's now 10 cores, 16 cores, 200 core systems. There's a lot of memory. 32 gigabytes is kind of more or less standard at this point. In disk space, there's terabytes of disk space. People complain about 512 gigabytes of data not being enough. A lot of the codes that we are interested in, might be distributed and decentralized. So they might span multiple machines. So you probably see that in the neural network training. And they also use specialized, a lot of the codes nowadays are using specialized hardware for certain tasks. So GPUs, for example, are specialized hardware to do vector arithmetic. So also the current hardware has not increased substantially in terms of serial performance over the past 10 years. So over the since 2007, the serial performance has been steady. Vectorized, which what I mean vector is like SIMD or single instruction multiple data, or sometimes you hear AVX or SSC instructions. Those has they've every few years they increase the vector size. So from the AVX2 is about 512 bits. Multi-threaded would give you also like some sort of performance, and then what we're after is kind of vectorized and threaded performance. So that's what we want the compiler to be able to generate, is vectorized code and multi-threaded code. The other thing that I think is useful for people to know is that if I look at a system, like this laptop, for example, the compute power is mostly so this is like C++ code. If I write C++ code, but if I write serial C++ code, I should get this like whatever 10 gigaflops or something performance. If I write it with multi-threaded, I would get 80 gigaflops. If I write it with the vector intrinsics, I would get 100 gigaflops or so. But the most power is in the GPU, and that's kind of what we're trying to do. Is initially what we're trying to do is give you this performance, and then eventually the GPU performance. It ends up that GPU code is more specialized, so you cannot write a lot of programs in GPUs. So the strategy for us from the compiler team is to provide tools for you to do program analysis, code generation, and type inferencing. And these are tools that is supposed to be, you can also use, so they would be like utilities that the compiler provides. And we're aiming to generate performance code and reduce magic. So instead of having, kind of magic rules, we would have sensible rules that can be explained clearly. The generated code, I think this is something useful, is the generated code can be used outside of the Wolfram language, and I think Connor showed that 2 days ago, where he was doing debugging, and he was doing debugging in LDB, and it was outside Mathematica. We're machines, modern and future hardware, so we're not interested for machines, machines from 10 years ago. People can opt in and opt out of certain optimizations or enable debugging. And then advanced users can write their own languages, essentially, their own embedded domain-specific languages from within the Mathematica, from within Wolfram. And then also people can intermix Mathematica with C and assembly and maybe LLVM. So the compiler is structured as a kind of a pipeline. So I'll go over each one. So initially what we do is we take Mathematica code. So this is stuff that you usually program in, and we translate it into kind of a lower level representation. This is still valid Mathematica code. It's just kind of doesn't have certain features. For example, increment does not exist. It's just implemented as a module, as a kind of a desugared form of increment. We then go from that code into an intermediate code, and that intermediate code is untyped. So this is what Tom said. This is what's called SSA form, or single static assignment form. We then do type inferencing on that intermediate representation to generate this type pool from IR. And then we generate, we generate LLVM or C++ or codes, and then the code is executed either on ARM or Intel or AMD hardware. So the AST, or the abstract syntax tree, is essentially an expr. And the expr allows you, so maybe I should zoom in. So this is we call this create mexpr, which just holds that expr in a data structure. And then you can do queries on it. So this is showing the expr information. So this is a list, and it has certain properties that you can query. Then you could do some transformations on that expr. And in here, what we're doing is, in the original program, there's two x's, and this x is bound to this module, and this x is bound to this module. So what we do is we just rename all the x's so that they're unique. So in here, it's clear now that this $1 is bound to here, and this x is bound to here. By the way, you can stop at any point and ask questions. We also have a way to do program analysis on the expressions. So one example is we can find which variables are not bound in that expression. So if I have x plus y and only x is bound, then I should expect the free variables to be y. These are kind of tools that we use. And then there's other transformation like function application, sometimes called beta reduction. So if I have a function, I should kind of like a function, and I apply z to it, I get a different, a new function where y is now bound to z. We also have on the expressions, we have a thing called macros. So these are similar to scheme or Lisp macros. And they work with a pattern language. So one example is I wanted to have an implementation of up to. So up to is a kind of a relatively new symbol, which gives you, essentially it's the same. But if I say take list up to 8, then it's if the list is smaller than 8, it's still a valid expression. So what it's doing is just computing the min of the value and the list. So I can define take, a macro on take that says take of list up to n is rewritten as take of list with the min of length and n. And now I can then say macro expand the expr, and I get a new expression where now this expression is rewritten as take list min of list and 8. The macro system can also be used to perform program optimizations and transformations. So a common optimization is called loop fusion, where if I have a map of a map, I can fuse the two functions and get a new a composition of these two functions. So I can define what composition means, what length of map of list is. Essentially, I don't really need to do map. I can just take the length of lists, so here, and then map of f of g of list is the composition of f of g mapped to the list. And I'm also doing something like map of f of take of map of g of list is this thing. I could just take the elements and then apply the map. And now if I define this function called map of myfun1, map of myfun2, take of map myfun3 list up to 8. Yeah.
It is only if there's no side effects.
Right. Yeah, assuming there's no side effects. Yeah. There's a side effect analysis that we run, but it won't fit on a slide. But now I have this sort of function, and if I execute this function kind of naively, I would go over this list. There's 3 loops that are going over the list, and now in this transformed code, I'm only iterating through the list one time. So, and I didn't have to write that much code to do that. So these are tools that we have in the compiler that we use. Now the intermediate representation is kind of also called IR, is something that's kind of like machine-independent assembly, where now you've lost a lot of information about Mathematica. There's no Mathematica construct. What you have are things like memory loads, memory stores, branches, and conditionals. So if I have this function, typed integer 64, and then this counter, and then I can, it translates into something that's a bit harder to, you don't recognize that as a Mathematica code, and it's more or less gibberish if you've not looked at these things for a while. But initially, you have you load an argument, then you jump to this guy, and then you have a set of instructions, and then you have a branch, a condition that says, if this is true, then jump to here, otherwise jump to the exit, and in the while body, it jumps to the condition again. So it becomes this sort of graph, that's kind of a loop. And then once this condition is false, it goes to this while exit. So the other thing, that's the Wolfram IR. The other thing is the type system. So the type system is, and this is something that's important, is that we wanted to make it independent, and we had previous iterations of this, but we wanted to make it, the new iteration, independent of the compilers, so no types are hard-coded. And there's a lot of presentations here that we're talking about types, proof theory, representation of different structures. The type system uses, essentially unification to infer missing types. So you essentially have a pattern, and you're trying to figure out what values satisfy this pattern. It supports things like abstract types, and I think one of the questions in Tom's talk was whether these are similar to type classes, and they are. So it's similar to type classes, and they're called different things in different languages. Some languages have different, they call them different things because they're slightly different, but they're more or less equivalent. They allow for type overlap. So this is, if you know Haskell types cannot overlap, and they must have the same number of arguments. So that's kind of relaxation from the Haskell type system. We allow sequences and recursion. We have some limited support of dependent types and type evaluations. And the reason why the type system is complicated or needs to be rich is because if you have a type system that is not rich, then you get this thing of you have code that should work, but you cannot represent it in the type system. So the code that can be well typed and works is small, and we want to maximize that as much as possible. So this kind of region where the program works but is not well typed is called the region of abysmal pain, because you kind of want it to work, but you have to kind of hack it, or you cannot express it in a certain way. And sometimes that's what a lot of this, like Scala and Haskell, they try and reduce or maximize this overlap as much as possible. So the type system is also organized in as a set of type classes or properties on types. So we have things like what happened to the graph? What happened? Sorry. Let me validate this again. So we have things like equal, and there's a set of functions, a set of types that inhabit equal, and a set of functions that are needed for to have the equality property. Things that are integrals, and they have quotients of mod and ceiling, and there's different types. So this allows us to organize types in kind of a structured way. So now I'm going to come up with some examples, which kind of stress test some of the compiler features. So the first example is compile time code generation. So I want to compute Fibonacci, and I want to do it at compile time rather than runtime. So in Mathematica, you could do that by saying with f equals Fibonacci, and then kind of embed that f in the function. So if I do that, then you get function that returns 55. Now, in the compiler, there's different ways of representing that same thing. One way of doing it is using macros. So if I have a macro that's called fib, I can define what fib of 0 means and fib of 1. And I can say fib of any integer is an evaluation to compute a Fibonacci. So if I then say macro expand of fib of 30 and then show the expression, I get this thing, which is computed at compile time. So this is, you don't pay the penalty if you inject that in the code to do it. Now you can also do this computation in the type system, and this is like, not pretty, but you could do it. And this is using dependent types. So if I say what the type of fib of 1 and 2 and 3 are type literals, and then I could say the type of Fibonacci of anything is, actually, this is not Fibonacci. This is factorial. Sorry. I renamed it, and I renamed it to the wrong thing. It used to be factorial. I thought it was Fibonacci, and then okay. But then you could say, fib of 3 evaluates to 6, and that's just using the type system. You can also do stuff that you could not do in Mathematica, which is, for example, if I want to generate vectorized code that's machine independent, I can write that in the type system. So in here, I'm writing an RGB to grayscale, and I'm using this type called SIMD vector. So this is kind of a machine vector, and then I can use total and some sort of compile intrinsics to generate SSE code, AVX, SSE3 code. And this will work, if I'm on, an ARM processor would generate Neon code or whatever the equivalent stuff in. If I'm on CUDA, I would generate the right stuff. So then you can write, stuff like, what dot means, what min means, and you get these kind of IRs. So the other thing that, the other thing that I wanted to look at was, some people are interested in, like doing auto differentiation or defining D in the compiler. So you could do that in the, again, you can do that in the macro system by defining some, some certain rules, like, an integer derivative is 0, and then, some sort of trig rules, and then, some sort of expansion rules, so plus of a of b. And then if you evaluate that, say, macro expand d of sine of x plus cosine of x with respect to x, you get, the subtractive cosine of x sine of x. So that's fine. And you can also do it in the type system. So, this is not something that you really want to type, but something you could do. There's other applications where you might want to do this sort of stuff, but you could do it in the type system as well. So I think that's it.
Why were you showing these macro and type implementations? Is that a good way to do it? Or?
That's one way of doing it. I mean, you could do it in a bunch of ways. I mean, the thing is, like, you could do it that way.
It sort of strikes me as sort of abuse. Like, but it's kind of
Right. In C++, I could define a Fibonacci at compile time using templates.
I think it's showing completeness of the.
Right.
It's showing completeness. I mean, probably for differentiation, you want to differentiate the program and differentiate the program steps and branches and things like that.
Right.
I think it shows completeness of what we're building. So,
I get that.
yeah, which is I'm sure it means a good thing. There's
Yeah.
no holes.
Not sure I was getting it.
I mean, the other thing is, like, sometimes you want to compute properties, and these properties are only defined on the types. They might not be defined on the variables, or they might not be present in the program. So, for example, for structured arrays, multiplying, two symmetric matrices produces a symmetric matrix. So that might be in the type language, but the program still is exactly the same. You and
Do you have utilities for the ASTs?
yeah.
Do passes?
Sure.
Yeah, everything is written as a pass in the compiler.
Pattern matcher. They have a pattern matcher. That's how the macro system is. They have a pattern matcher that works.
Right.
Sorry?
To run other passes?
Yeah,
Oh yeah.
yeah. We define passes all the time.
We're discussing a pass for
Doing closure conversion right now.
closure conversion.
Right.
That's very cool.
You can assign properties on the expr that don't, you can say, oh, I visited this expression.
Yeah, so adding metadata.
Right.
That's the problem with regular expressions. Sure.
Yeah. Yeah, we have
We have a visitor.
post order, traversal, pre-order, topological order, a bunch of orders. Yeah.
This is a real thing. The other thing is, I think, this is, and I think having a workshop on like how to write passes as well. I think that's And the rule with these passives is you make them all very simple. You know, if they're too complicated, then
I tell Tom.
you know, not to do it. But you know, instead of calculating three things, you have
I used to work with a Stanford compiler group, you know, and there's a lot of work building these intermediate infrastructure that you want to amortize and share.
Absolutely.
Because that's a pain in the ass.
Absolutely.
Actual research that you want to do.
Lift it out.
Compiler, for instance.
Lift the things out in separate places.
Right.
That
So
you
if
can
we can make
reuse
this,
it.
you know,
Abstraction.
so we have a hell of a lot better infrastructure in the Stanford compiler group.
Sure.
You know, in terms of building interesting optimization paths.
We can look at all the sort of Neanderthal dead ends that maybe people regarded out, so we can learn them.
The other thing is we're breaking, so we started this with a type system. We're breaking some of the stuff that could be shared across different projects and could be used.
Independently.
Right. So one is the AST. We have it as separate, it's a separate project from the compiler. It used to be in the compiler, now it's a separate repository. The type system is completely independent. There's other parts that.
There's a dependency, the compiler has a dependency on the type system, but the type system has no dependency. So even the names of the types, make your own. Have nice Swedish.
I mean, that's what I did here, is I created my own.
But that means that we could define, for instance, sort of a super optimizing compiler. When it's work, it's not normally in your everyday kind of work. You can't afford to spend that time.
Right.
But there could be cases where that's crucial.
Right.
Really sort of go to town.
Right.
Absolutely.
Or verification for that matter, right?
Yep.
Any more?
We have constant needs. This is like we're having we have constant needs to analyze code and understand what it does for different sorts of things. And this is the framework for doing it. Because this is so one of the output types for the like we can output CUDA bytecode or JavaScript or something. And one of the outputs, of course, could be Wolfram language code. Just rewrite your Wolfram language code in a way where you started to understand it and improve it. No. But for example, supposing this was a concrete case, we have these, raw, packed array objects. So you're adding a whole load of packed arrays together, and the one, adding 20 of them together. The one in the middle is like a complex double, and the other ones are like, they're like integers. You want to make sure that you maintain the right order, but everything turns into a complex double. This is the framework to do that. And it could just rewrite your plus expression, give you another plus expression that'll do that. It'll give you a function that'll do that. So then you can cache the function, and then next time round, you won't have to pay the price.
I mean, the other thing is that sometimes performant code is not the code that you want to write. So one example is sort. I mean, the performance code would be compute ordering and then do part on the ordering, right? But nobody wants to write that because it's 2 lines instead of 1 line. So we could, you can write sort and then it gets translated into ordering if you really want to. All right, so I think that's pretty much it.